Today we're going to talk about the traveling salesperson problem. Okay, so now let's dive into the assignment stuff. So first, linked list is a really important topic, and we started to talk about it a little bit in Precept. In the interest of time, I'm not going to go into a lot of detail about linked lists. So this assignment used a slightly more complex, and I'm using quotes about complex because you'll find out that circular lists actually make lists easier. But what you would need to do before you start working with these circular lists that are a little bit circular in logic is to understand the normal regular list. So here's just an example of a list. It's part of the linked list slides that I'm going to put on the class meeting page. And it just shows you an example. So linked lists have two elements to them. They have a node class. So node is just a name that we use. It's not any special keyword. And this node class is going to be containing a value of the list. And so there's two things that are typically very important in this node class. The value itself. So that's stored in the instance of a variable called value. And then the pointer to the next element in this chain of information. And that pointer, that reference to the next element is usually called next. So then what's involved is understanding how these nodes are chained together. So by making each one of them have their next point to the next one. So n1.next is going to have 2. That's creating this arrow. n2.next is going to have n3. So that's creating this arrow. And what's important in linked lists is that we chain each of these elements together, but we also need to know where the lists start, because otherwise that chain just exists in the ether. So there's always going to be a starting point, at least one starting point called first, that connects us to the first part of the list. So what is the traveling salesperson problem? The traveling salesperson problem is you have a set of n cities, and you want to drive to each of these n cities using the least amount of mileage possible. So what that means in practice is it means you need to find the circuit or tour. So it means from a starting point to all of the cities and back to that starting point. So think of your headquarters or your home. And you have to visit every single one of the cities. So here's one circuit, one possible solution. But as you can see, there are many, many, many possible solutions. So one question that we would ask ourselves is how many possible solutions are there? So here I have 5 cities, and I've already found 4 tours, but are there more? And yes, there are. The number of possible solutions are all of the permutations, so the n factorial orderings of the city, divided by the number of directions, because we could take them in one direction or the other. So divided by 2, and divided by all of the starting points that we could have. So overall, we have 1 divided by 2 times n minus 1 factorial, which is, if we're using gross approximations, something on the order of n to the exponential n. There's some other factors there, but it's about that order, and it's exponential in nature. So exponential in nature means that it seems like this would be an easy problem, but there's really a lot of possibilities. And here we only have 5 cities. So in all of these possibilities, which one do we think is the most efficient in terms of size? So I'll give you a couple seconds to look here. So the most efficient one is going to be the one where the string around the cities is the tautest. So it's going to be that one over there. So you may tell yourself, oh, identifying that one out of a lineup of 25, or I forget how many, it's not that challenging. But you need to realize that, these are only toy problems. In real life, the instances of the TSP that really matter are going to have a smorgasbord of actual cities, of actual points. So here's an example of an actual real-life TSP of 50,000 sites around the US, and it took an enormous amount of computing power to come up with this shortest path, this shortest TSP. So this is the least amount of driving you could do to go to each of these 50,000 sites in one driving tour across the US. Okay, so more generally, these types of problems are called combinatorial optimization problems, and they're really important. These combinatorial optimization problems are characterized by the fact that the only way to find the optimum for this TSP solution is to look at all possibilities, evaluate every individual possibility until you found the best one. So as you can see, this is really a recipe for disaster because on the one hand, there's a ginormous number of possibilities, and on the other hand, the only way to find the best one is to look at them all. So that means that you have an incredible amount of work to solve this TSP problem if you really want to get the best answer. So to give you an example, the possibilities grow exponentially, and so in practice, since the growth of the amount of time we're going to spend really grows quickly, so after only 16 or 17, we would be out of the ability for us to solve it on one of our computers. What this means in practice is that instead of trying to solve these problems exactly, our focus is going to be on trying to find good enough heuristics. So we've given up on finding the best TSP. What we're going to try to do now is finding TSPs that are good enough, finding rules to improve on TSPs, and finding solutions that we can live with. So the TSP with 50,000 sites is done using existing roads. Yeah. So more generally, the reason why TSP is so important is because this problem I just described to you, it's really not just TSP, it's a whole class of problems. And those problems are called NP-hard. They all look like this. They're all problems that are really useful, that have a lot of possibilities, and the only way to solve them is to looking at all of these possibilities. So that's what makes these NP problems hard, NP-hard, and that's why we keep hearing about this factorial order of growth. That's when we were looking at performance and looking at all of the possible order of growth, we had a special room for n factorial, because all of these problems have the same issue. Okay, so now that we've understood that we need to focus not on finding the best answer, but finding a good answer, I'm going to introduce the two heuristics that we're going to study in this assignment. So since we can't build the best TSP, we're going to look at two ways of building good enough TSPs. So the first optimization, the first heuristics that we can think about is the nearest neighbor heuristic. The nearest neighbor heuristic is quite natural. So you have these 3 points, these existing cities, and now you're going to try to see, if you add the city in blue, which neighbors, which cities are closest geographically to that new point that you're adding. So to do that, we just measure the distance from that blue point to each one of the neighboring cities. So we measure the distance from blue to 1, the distance from blue to 2, the distance from blue to 3, and we pick the points that's the closest to decide that we're going to insert blue right after that point. So here in this example, as you can tell, I'm sure, the nearest neighbor is point number 2. So what we're going to do is we're going to have point 1, point 2, and then we're inserting point blue right after 2, which is its closest neighbor. So the tour that we get as a result of that has this crossing. This may not sound smart to you to have a crossing, but it's the logical result of following this one heuristic. So we can see this heuristic makes sense, but maybe sometimes it ends up in not that great of outcomes. Okay? But that's okay. As we said, we can't find the best solution, so we have to deal with what we've got. So the next heuristic that we can think of is the smallest increase heuristic. So the smallest heuristic, smallest increase heuristic is another iteration of the above heuristic that's trying to ask ourselves, now wait a minute, how can we avoid sort of silly things like this where we're inserting something and we know it's not the right answer? Well, the smallest increase, the idea is we select a point that minimizes how much we increase the tour. So it's like, imagine you have all your points and you have a rubber band, and it's figuring out which points where inserting that rubber band would result in the least extension of it. So here again, same examples. We have these 3 starting points in the same blue point, and now we're measuring how much difference there would be of us inserting that point in between any 2 other points. So the way that we do that is we measure the distance, the path, if we didn't have that point. So that's before the insertion. And then we measure the distance to that point. And we measure this minus this. So that gives us an idea of the increase when we add the point in between 2 and 1. So again here, in 1, 2, 3, we're going to measure the increase of adding the point between 2 and 3. So before we were adding that point, we had this edge, and after we have it, we're going to have this path. So we're measuring this minus this to measure how much the increase will affect the overall tour. So when we've done these operations, we notice that the best place to insert the points is here. And we result with this final tour at the end. So, wait, yeah, sorry. We realized that we inserted right between these points to result in this increase. So we have this increase at the end. Sorry for misspeaking. So one of the things to notice here is that with this heuristic, at least in this toy example, what we're avoiding is these types of crossing which are obviously not the right call. Okay, but it's going to be very interesting in your implementation when you're running it on big data sets to see if at the end the top one or the low one is the best performing one. For nearest neighbor, do we need to consider the total distance that would be added if you add a point after the last one? So I'm not sure I understand this question. So for nearest neighbor, no, you don't. Oh no, I do understand this question actually. For nearest neighbor, we don't consider the increase at all. We don't consider the total distance that would be added. The only thing that we consider is the distance to each individual point. It's a very, very local choice. It's a very narrow decision, and it has predictable consequences that aren't good. How many points should you look at to look for the nearest neighbor? All new points. Yes. For the nearest neighbor, we look at all new points. When we're given a new point, we have no way of knowing which of the existing n-1 point it would be closest to. So the only way that we can assess that is by comparing that point to all of the ones that have come before. Yes, for smallest increase, don't all 3 triangles result in the same end result? No, for smallest increase, not all 3 triangles result in the same amount of increase. As you can see here, if you made the calculation, you'd find that this one has a clear smallest increase compared to all of the other ones. So what we're comparing is so I guess this question is asking a very good thing. What we're comparing is not whether the increase between this and this is larger. What we're measuring is the increase in size that we have by subtracting this by this, and we're comparing it across all possible increases that we could do. So we measure the overall cost to the tour of all of these possible increases, and once we've measured them all, we decide where we should be making our call. Which insertion would result in the lowest overall increase of the tour. Where did the blue point come from? Where did the blue point come from? Thank you so much. That's a very good question. So the way that we're proceeding to build this TSP is we're given endpoints. And instead of just computing endpoints, the way we proceed is simply by saying, well, if from a given tour I know how to add an additional tour, then the way to solve the problem is to just start with an empty tour and add each of the endpoints that I'm asked to process. So the blue point is just modeling the way that you're going to be building your tour, which is by starting from 0 and adding the points one by one. This is an excellent question. For all heuristic, does the program have to compare against all of the points that are to come? So for all heuristics, the point that you're inserting has to compare with all of the previous points. So every time that you do an insertion, you have to make at least a linear number of operations. No. So do we implement both? Yes, you have to implement both. The assignment specs want you to implement both and compare their efficiency. That's one of the points of the assignment. How could you insert a point between 1 and 3, like in the third triangle? Wouldn't that violate the order you already have? I'm not quite so in... So, no, it doesn't violate the order. So point blue is point 4. So the numbering is just it's just a numbering for us to discuss the point. There's no constraint of order in the numbering. The numbers have no important significance that we need to respect. Okay, so I'm going to move on now. So this TSP problem is incredibly useful. It's one of the most important problems that you're thinking about, that you're working on. None of the applications you've worked in an assignment have had as many ramifications as TSP. So all of the NP hard problems were really unlucky because all of the NP hard problems have huge optimizations. That's why quantum computing is such a vibrant research field, because everybody in quantum computing knows that if we can crack the quantum computing nut, the NP hard problems will be a lot easier to solve, and somebody is going to make a bucket load of money, like a huge amount of money, because all of these problems save a lot of money. So, for instance, TSP is used to create school busing routes. It's used to plan vehicle routing in cities. So when you order an Amazon package, you're sending packages throughout cities and suburban spaces, and to make sure that the gas mileage of all of these vehicles is as low as possible so that Amazon can make as big of a profit, they use huge instances of the TSP problem. So TSP occurs in printed circuits to minimize the amount of soldering that we do, to optimize the length of the circuits so that there's less loss of the electric current and heat. And it has many applications in genomics, in medicine, in drones. So this is a really, really important problem by a landmark. It's the most important problem you'll think about in this course. So now let's delve into some specifics of the assignment. So your job is to implement the Tor API. So what is the Tor API? The Tor API takes an array of points, such as this one, and it will provide a tour of those points. So your job is to implement this tour of points. That tour, it could have crossings or not. The crossings are very normal with the nearest neighbor implementation. So this is the API. You have to implement two constructors, one that creates an empty tour. So that's the one that you're going to be using in actuality, because you're going to be creating an empty tour and then adding all of these points one by one until they're all added. And then there's a second constructor that creates a 4-point tour. So the point of that constructor is only for debugging. The whole point of that constructor is to make sure that while you're building your program, you're creating mock tours and you're seeing how they behave. So here, in the same way that in my examples here, I had, crap, I shouldn't have rewound so far. Yeah, so just in this case here, I had an example with 3 points and I saw whether the heuristics were working correctly. You should be creating a tour with 4 points and seeing whether your heuristics are working correctly. So then the methods that you have to implement are size, length, which just provide information on your class. And importantly, these two methods, insert nearest and insert smallest. So insert nearest is going to be the nearest neighbor heuristic, and insert smallest is going to be the smallest neighbor, the smallest increase heuristics. Of course, your class should work even if we alternate calls between the two of them. Okay? And then toString and draw are two methods that are going to be really important for debugging. So make sure that you do toString first. So behind the scenes, this is what your internal structure is going to look like. So as I said, this is the circular version of linked list. So instead of having a pointer that is called first, since the list is circular, we're going to call this pointer that points at some point of the list head. It doesn't really matter which node it points to, but it just makes it's necessary to have at least one node. So each head is going to point to a node object, and that node object is going to have two pieces of information. The first piece of information is the point that it is connected to. In our examples of lists, we always had lists that stored numbers, so primitive data types, and they were stored directly in the node. Here we're going to have a point instance, and we're going to link at it with a reference. So these are the points that are provided to you. The second information that each node is going to be connected to is the next node in the circular list. And so the next node in the circular list. So the assignment inputs and goals are the following. You have to implement the tor.java class. You are provided with the point.java class, the node class, and several test clients and sample datasets to check whether your implementation is correct. So we're giving you a lot of the beginning code because what we are really trying to check is whether you are able to manipulate the circular list implementation, whether you're able to make insertions left and right in the circular list. So the assignment introduces you to linked lists. Can you use a data type that is provided to you? Can you use the point class? Can you use a private node type? Can you traverse a list? So to traverse the list, you might need to make use of size or length to do a while list. What about when there are different base cases? So tour.string is going to have to handle different possibilities differently. And can you modify a circular list? It's not the same thing as is involved with a linked list. So I want to call your attention to a tool that's going to be your best friend in this assignment. It's TSPVisualizer. So TSPVisualizer is a client that, given your code, is going to, so given your code, that means your Tor class and your draw method is going to provide you with an easy way of testing it. So you have a couple commands. One is to toggle to nearest number and to toggle to smallest increase. M is the draw mode and Q is quit. So the test client provided will do the following things. It will set the pen color, and you can take a starting point of set of points and then output what the text output is on the console, and you will check that output with the visual output that you see. So on the screen, starting from nothing, you're going to click on the screen to create points and see what kind of tour your program does. So that will be really useful to see whether your implementations are correct. So here it's providing you an example of the nearest neighbor heuristic, and in blue we will see how that heuristic would be different with smallest increase. So this is the text input that would happen at the same time so that you can verify both visually and in the text output whether the points that you're getting make sense. Okay, and so here in blue shows you the contrast between the nearest neighbor and smallest increase. Okay. No. So question, should the head also contain a point, or is it separate from the tour? No, the head only contains a reference to a node. It contains nothing else. Are the heuristics implemented as different methods within the same class? So yes, I hope I've shown you that. And if you want extra credit, I think that we suggest different heuristics that you can implement separately in a different class. Okay. So now, so this is, again, an example of how you can see the differences between the two heuristics. So one challenge for the board is, can you systematically build bad sequences of points for nearest neighbor heuristics? And if you are curious and if you want to challenge yourself a little bit, think of a program that will specifically build instances or sequences of points that will be really bad for nearest neighbor. Okay, so now tips and tricks. The point API. So there's no way to access the x and y coordinate of a point class, and that's intentional. So challenge of the board, can you think of a way to use either math-based or text-based way of extracting the coordinates from the points? So in tour.length, to measure the perimeter of the tour, you use point.distance2. In tour.string, to list the coordinates of all points, you use point.toString. And in tour.draw, to draw the outline of the tour, you're going to use point.drawTo. So these are the three ways that you're going to get around the fact that the point API, once a point has been created, you cannot recover its x and y coordinate. So you have to use this API to be able to get to what you want. And that's one of the challenges of this assignment is, if we restrict the information that you have access to, are you able to use an API in the right way? So next, in the circular linked list, this is what the circular linked list is going to look like. And this is the kind of way that you should be testing how it works. So as I said, you want to use the constructor that has 4 points. You want to assign points that you are predicting, and you want to make sure that the output matches what you expect. Okay, so make sure that you understand how things are represented inside, and make sure that you understand what should be outputted. That's part of the theme that we've been repeating of, it's really important to predict what your function should be returning or what your program should be doing before you actually test it. So this is a side note that you can look at in the slides in more details, but essentially it's very helpful to create helper functions to make many, many tests. So in this case, I have a test that just makes sure that these 4 points create a square. And the only thing that I provide to this create square function is the size of the square, and it creates the 4 points for me. So that's anything that makes testing, generating test case less tedious is really a good investment of your time. So helper functions for insertion. Modularity is often very desirable, part of the point of functions. Helper functions can be very useful to make sure that you don't have to face the same problems many times. So to avoid duplicating the same logics in several places, you can create a helper method called insert point after. And that will handle sort of all of the tricky list code, so that at some point, once you dealt with it, you can focus on the heuristics. To make calling the code clearer, you can also create a compute increase method so that your code for the smallest increase is easier to understand. So here, let's just quickly review the edge case and bad cases. And I might have to skip a few slides. So what are the edge cases and the base cases that you have to deal with the circular list? So the easy case is when you have many nodes. This is what it looks like. Correctly identifying what the edge cases are can save you a lot of time. So in this case, the clear edge case is when you have 0 nodes. So again, that's sort of like in the symbol tables in Markov, the case between when you already have the k-gram in the symbol table and when you need to insert it for the first time. These are the edge cases that are a little bit trickier. So thinking about how to deal with them and whether 0 nodes and 1 nodes are really separate cases or can be treated the same will save you some time. One of the tips that I will introduce to you is that you can use a variant of a construct that we've used. So you know the for loop, you know the while loop, but we have also the do while loop. And you may find that it's very useful to manipulate circular lists without having repeated code. Okay, so this is what your TSP approximation should look like in pseudocode. You look for every point, you find the point that you have to insert, you create flag variables, best value so far, and best candidate that you insert to null. You have to pick the default value carefully, and then you go through all the points that have already been inserted in your tour, and you measure whether they are the best candidate for this particular increase. And as you update this best candidate, at the end you know where you should be making your insertion. So this shows you something that people have asked in these questions, which is, do we have to look at all of the points? And yes, you do. You have to look at all of the points that are already in the tour when you're inserting a new one. So I just want to give you a cool example of a real-world application of a possible optimization that you could be doing. So USP has actually found an optimization of TSP that avoids making right turns, because when you're making a right turn at an intersection, you have to wait for the traffic to clear. Whether often a left turn, you can make it as soon as you are able to without waiting for a light. So by creating TSPs that optimize and create more left turns than right turns, USP has been able to save a considerable amount on gas and on delivery time. So this will skip. So in the last 2 minutes, I just want to give you a last tip for one of the hardest and newest part of the assignment, which is the analysis that we're asking you to do. So the analysis is going to be in two parts. First, you have to write a little bit of code to generate a lot of data points. I'm a millennial, you are at the boundary, and one of the things that defines me is that I really, really like data. And I know that people in my generation really like data. So here's your opportunity at generating data about your program to see how it performs. So generating data is making sure that you have, for at irregular intervals of n, you measure every parameter of your assignment. So the length of the tour, the time that it took to build it so far, the length of the smallest, and the time that it took to insert the smallest so far. That will help you compare everything. So the last thing that I want to do, that I want to say, is that you are going to be applying the doubling method to compute the running time of this. So quick recap of the running method. We assume the function is polynomial. We pick a point and the same point doubled. And we know that by using these 2 points, we're going to be able to deduce the factor A, which is the constant factor, and the factor B, which is the exponential factor of this area of growth. So to create this data set, here are the types of method that you're going to be using. Creating a set of n random points, randomly timing these n random points, and popping out the results of timing these n random points. And you're going to do that with 500 random point, then 1,000 random point, then 15,000 random point, and so on and so on. So you're going to output this data as a comma-separated value. And here's a really good time-saving trick that I'm giving you. I think that the best way of then analyzing this data, once you've outputted it as a comma-separated value field, is to copy-paste that whole text, paste it at the top of a Google spreadsheet, and then as you've selected that text, you click here, and you do split text to columns. So then you're going to have this beautiful spreadsheet in Google Spreadsheets that's going to make it a lot easier for you to compute your formulas. So here, this is the formula of the doubling method. I just need to encode it. I sort of truncated the formula so you don't get the whole answer and you have to think a little bit. But essentially, once I've done that, I can compute the runtimes, the doubling method for everything, and see what it actually converges to. And you can see that as I take more points, it converges towards the same value. So the more points that you take, the more that you average, the more accurate it's going to be. So I encourage you to do a lot of calculations and to compute the average of these calculations as much as you can. Finally, a question for the curious. Compute the ratio of the length of the tour created with the nearest heuristics and with the smallest increased heuristics to see whether they're proportionally better in a certain term from one another. So is the smallest increase 1.5 times better than the nearest neighbor, 1.3 times, this is something that you can find out, and it's a really cool fact to know. Okay, finally, best advice, have fun. And there's no time, but I'll try to follow up on Ed if you have any questions.